Wish it was a lot longer, but what's it, about 4 or 5 more weeks, then we're done for a summer. So sounds pretty good to me. So we have, 4 or 5 more weeks left. I went ahead and I got all the exams graded already. I got those knocked out before Easter. Those are all posted in my math lab already. So those grades are updated, and your grade in my math lab is your current grade in the class. The only issue, so not everyone has taken the exam yet. So I can't hand out the exam and give feedback on it until everyone has taken the exam. So I think by that time frame, I will be handing out the exams a week from today. So that's just how it works out. If you do imperatively want to see your exam grade, you can set up an office meeting with me and we can talk about it then. I'm going to reserve passing it out until everyone's taken it. So, and I was thinking about, so I was also thinking about whatever your grade is in there, I wanted to apply so sometimes I curve exams. The curve that I see for this class based off of everything is a 1% curve. I have not applied that yet. I will be applying that later on today. So your grade in there will be bumped up by 1 whole percentage point. So that will be the curve that I see fit based off of the distribution of the grades in this class. Besides for that, does anyone have any questions before we move on to the final unit of material? If not, let's go ahead and do exactly that. Now, provided I finish section 8.1 today, that homework's going to be due Wednesday. If not, I'll of course push it back a day or two. And for these remaining 7 assignments, that will pretty much encompass the majority, if not the entirety of the final exam. So depending on how much information we get out of these final 7 sections, that may make up the final exam. I do have the right to make the final exam cumulative, but if there's enough information in these 7 sections, then the final exam will not be cumulative. So that means if the stuff before may have tripped you up, you might not have to worry about it come to the final exam. So just keep in mind, I do, according to the syllabus, have the right to make the final cumulative. So I suppose let's see what all of these remaining sections have to deal with in this new chapter on sampling distributions. Now, what we're moving on to is something a little bit more practical in the way that statisticians look at information. We're going to, of course, as the name of the chapter implies, look at sampling, which, of course, sampling means if you want to study a population, then you find a sample, a subset of that population, and you survey them on something. It doesn't matter, pretty much anything. You can ask what their gender is, you can ask what their age is, their heights and weights, and this and that, it doesn't matter. But really what we want to do, so finding one sample may not be too helpful because one sample may not be truly representative of the population. So you might think, all right, well, how do we know that we've chosen a good sample? How do we know that? And well, there's not really any deterministic way of figuring that out, because if you knew that, then you wouldn't need to take a sample in the first place. So instead, what statisticians do, they'll take a whole bunch of samples. They'll take a lot of samples. So you want to figure out the average height of Southeastern students, you might go out and find a sample of 10 students, find their heights, and figure out the average height. And then you might think, all right, that sample may or may not be biased. Let's go out and do that study again. So you go out a different day. You interview 10 other students. Do it again. And then you go out another day. You survey 10 students. And what this does for each time you collect a sample, what you're doing is, well, with that sample, one thing you're doing is collecting the mean. And then at the end of the day, that mean, you could take the mean and find the average of the averages. So what you're doing is you're using the samples to get a nice diverse collection of information from your population, but you're not just relying on one sample, you're relying on a whole bunch of samples. You go out and do the study again and again and again and again. And this will give you some centralized idea of what your data values should look like. So this ultimately, this idea of multiple sampling leads up to sampling distributions. So that means that with the samples that you collect, you ultimately are looking at the numbers that result from them as a distribution. So you'll see, we've talked about distributions previously, and it's basically, you're going to see a lot of recurring information, but it's going to be applied to the information that results from taking samples a bunch of times and finding a statistic. Now, a statistic, you might remember a statistic and a parameter from the very beginning of this class. A statistic, not statistics the course, but a statistic as a measure. It's a measure that corresponds to a sample. And we're going to be looking at a lot of those. In this section, we'll be looking at the sample mean. The sample, so remember sample and statistic. Mean is, of course, the average. So basically, we're going to be looking at the average of the averages and the standard deviation of the averages. So that's going to be our data set, a collection of averages. So kind of interesting. It'll take a few examples to really understand this, and I do have a visual example as well. So basically what we're trying to do, when I say the distribution of the sample mean, we want to describe the distribution, which means the shape, the center, and the spread. So shape meaning, is it a normal distribution? Does it have a nice bell curve? The center meaning, what's the measure of central tendency? What's the average of the averages? And the spread just means the standard deviation of the sample mean. So that's what I refer to when I say the distribution. We'll be studying those characteristics throughout this section. And again, you'll see a lot of recurring themes that you have seen in the last chapter. So sampling distribution in general is this process applied to any statistical measure. And in this section, we care mainly about the sampling distribution of the sample mean. Now, we have the sample mean, and it also helps to know perhaps the population mean and standard deviation. Some of those are reserved variable names. Remember, the Greek letters refer to populations. And so what we're trying to do is extrapolate information from the population. So I kind of described the process here a moment ago. What statisticians do, they figure out a simple random sample of size n. So go out and interview 10 people. What are your heights? And then they figure out the sample mean from those 10 people. Okay, the average height is 70 inches. But then they think, is that a reasonable average height? I don't know. Let's go out and do the study again. All right, so you go out and interview 10 more people, and you get that the average height is 68 inches. All right, well, we have 70 and 68. We trust either of those numbers? I don't know. Let's do this study again. They will do it again and again and again. Normally, it's recommended that you do it at least 30 times, at least according to the scope of this book. I just wrote here a feasible number of trials, ultimately, is what we're doing, and it gives a sense of the distribution. You will get a whole bunch of averages, and then you find the average of those averages to give you a true idea of, well, what average height do I get the majority of the time, or about what average height? Now we start getting into something a little bit more formulaic. As you see, there's a lot of definitions, but we are now focusing on distributions of the mean, which is kind of strange. Normally the mean is one number, but now we're treating the mean as a variable. And with this, the mean's going to be very easy in this chapter. Now, you may remember X bar representing the sample mean. And mu, the Greek letter mu, is the population mean. So notice how the mean of the sample mean, yes, it's a lot of averages going on here, is simply derived from the population mean. They're going to give you in these problems the population mean and the population standard deviation. And so the mean of the sample distribution is just the mean of the population. So it sounds, the verbiage is all over the place, but the mean for the sample distribution is derived from the mean of the population. It actually works out a lot easier than it sounds. So in other words, the mean is the mean, which is going to make more sense when we look at examples. The standard deviation is a little different though. The standard deviation for this collection of means that we have is not going to be derived from the population. It's based off of that, but there's a little formula to it. If we know the standard deviation of the population, all you have to do is divide that by the square root of the number of, the size of your sample. So basically, they will tell you the population standard deviation. And if you went out and interviewed 10 people for each trial, then you would divide by the square root of 10. That's it. So it's not a difficult formula, but it is a nuance that we need to keep in mind. It's also known as a degree of freedom. It's n degrees of freedom, but you don't have to know that. You might also see it referred to as the standard error of the mean. And notice the notation is a sigma, and this might be hard to see. But these variables here have a subscript, so a small variable in the bottom right of the variable name. The subscript is x with the bar on top. So what these mean is, what these represent are, it's the mean corresponding to the sample mean, which again is weird. We have a whole bunch of sample means and we're trying to find the average of the means. And then the standard deviation of the sample means. Again, we have a whole bunch of sample means and we're trying to figure out the standard deviation. Now, what I want to do is kind of explain, oh, and also, last point here. As your sample size of n increases, so the more people you interview, your standard error decreases. This makes sense because as you interview more people, you get a more distinct idea of what the expected value should be for those sample averages. Now, how this is normally applied in practice, so the textbook gives a good example of this. So one thing, maybe you want to figure out the average IQ of Americans. Well, how do you figure that out? Well, in this study, so they use Excel here. And so each row here would represent 9 people they went out and figured out the IQ score of. And then they figured out the average for each of them. So this is what they would do in practice. So That's 9 people that they went out and figured out the average or the IQ score of, and then they found the average for that sample. And then they thought, all right, well, can we trust that average? Let's do the study again. Do the study again with 9 more people. They do it again and again and again and again. And they keep finding averages again and again and again. Those are the sample means, which are just numbers, which you can then find the average of. And the standard deviation of. That's a data set. That is a data set of, it just so happens that it's a data set of sample means. And that might or might not give a more clear representation of what's going on here. It's kind of dense information, but the computations work out very nicely. Also, if the population, not the samples, but if the population is a normal random variable, then the collection of the sample means will also be normally distributed, which is a pretty nice bit of information. So it means that the sample means will be normally distributed if the population is normally distributed. So IQ scores are naturally normally distributed, which means those sample means, that data set, will be assumed to be normally distributed. So here's an example. Again, the verbiage is dense, but the computations are very easy. So here, for example, 1, so let's go back to this idea of IQ scores. Let's say that, so they're just telling us the average IQ score, the population, is 100, and the standard deviation is 15. They just tell us that for the whole population, nothing about samples, just the whole population. Just assume everyone in America, they somehow figured it out. So suppose that we go out and interview 10 people. And what we're going to do is, or 10 groups of people, and we're going to figure out the mean and standard deviation of the sampling distribution. So now, what did they give us? They gave us the mean. So they gave us the population mean. They gave us sigma, 15, which is the population standard deviation. And they gave us a sample size. And we're going to use all of this to determine, so they're asking for the mean and the standard deviation of the sampling distribution. So they're not asking for that of the population. They want the mean and standard deviation of the sampling distribution. So in other words, what they want, so we need to find mu of x bar. So we're trying to find the mean of the sample means. Again, very dense stuff. And we also need to figure out the standard deviation of the sample means. That's what we're trying to find here. We're given everything on the left, find the stuff on the right. Now, the mean of the sample means, simply, well, if we scroll up, it's right here. It just says that the sample mean, or the mean of the sample means, is derived from the mean of the population. What was the mean of the population? 100. Boom, you already have the mean of the sample means. It's that easy. You don't have to do any computation for that. You already have it. Now the standard deviation almost works that same exact way. The standard deviation of the population is 15, but we have to divide by some degrees of freedom, is what it's called. The formula, it's on the top of the screen here. I'm highlighting it in red. It says take the old standard deviation, which was 15, and divide that by the square root of n, or our sample size, which is 10. Now it says here, there was one problem in your homework that said type an exact answer using radicals as needed. So they don't even want us to simplify. There's one that does and one that doesn't. If it wants you to use radicals, radical means, well, in this case, square roots, then your answer would be exactly what I just wrote down. Or if you needed to throw this in your calculator and find a decimal approximation, hopefully you all know how to do square roots in the calculator by now. 15 divided by the square root of 10. If you needed that, 4.7434. They'll probably ask you to round to 2 decimal places, but there's some extra ones. So again, it's kind of dense understanding, but very simple computations. So the mean of the standard means is 100 as derived from the population mean, and the standard deviation of these sample means is, or in other words, the standard error is 15 over the square root of 10, which is straight from the formula, or just 4.7434 about. Does anyone have any questions before I move on to the next stuff? If not, so one point I made, and it's at the top of the screen right now, if if the population is normally distributed, then your sample means are guaranteed to be normally distributed. However, your population doesn't need to be normally distributed for this to be true. If you take, well, we'll talk about how many here momentarily, but if you take a certain number of, if you do a certain number of trials, then what you will end up finding out is that the sample means will always be normally distributed, regardless of whether your population is normally distributed or not. Because what you will keep finding is that the values you will find pretty much a central value, and then values that slowly stray away from that center. So it's a pretty interesting thing that comes from this idea of a central limit theorem. So what this says is that in this section, we do not need the assumption of normality, because the derivation of the mean and the standard deviation of the sample means will always work out to be normal, regardless of if the population is normal or not. Regardless of the shape of the population, the sampling distributions of the mean is, they say approximately normal as you do the study more and more with different samples, more and more samples. Now, in this class, in this section, we're going to assume that you need at least 30 trials. It does say down here, if the distribution is unknown or not normal, we need a sample size greater than or equal to 30. That's going to pop up on a few of your homework questions, so make sure you notice that. So you require about 30 trials. And that's going to pop up in a few places randomly in your homework. So make sure you're aware of that threshold of 30. Now, if your population is normally distributed, this idea of 30 goes out the window. If your population is normal, then your sample means are already normal no matter what. If your population's not normally distributed, then you don't have that assumption for free, but instead you have to do this study at least 30 times. then you get normality. That's what this all is encapsulating to say. So again, a lot of verbiage, but again, the computations are pretty easy. Now, as I move on a little bit further, I want to go back to that example from the textbook. You have a collection of averages, and what you can do with all of these averages for each sample that you studied is, well, you can put them in a histogram. So all these averages you got from each sample, you can make a histogram out of it. So we've made histograms before, and that's what they did here. And so that histogram is normal. It's got a bell shape to it. And when you can model it that way, you get a lot of assumptions for free. So despite what the population involves, the averages, the sample means, will always have a normal distribution to them. So with this, we get a lot of neat properties from that we can utilize. And so here's another example. So this is pretty much, they already did the work for us. Let's say that they already found all the averages from each one of the samples they did, and then they made a histogram of that, similar to what I just showed you. And this is exactly what shows up. So this is the sampling distribution. Nothing about populations. They already did all the population work for us. And they skipped straight to the sampling distribution. This is sampling distribution of the sample mean. So when they ask for the mean of the sample means, well, we just read this graph like we did in the previous chapter. So I'll wake you all up a little bit. What is the mean here? 70. Yeah, it's easy. It's the one right in the middle. And so the standard deviation of the sample means, you don't have to do the formula. Well, we couldn't do the formula because we don't know any information about the population. They skipped all that work for us. They just gave us the graph of everything simplified. So what is the standard deviation here? 30. Yeah, it's 30. Yeah, it's any distance from the mean to the next step. 70 to 100, what's that difference? It's 30. That's just 100 minus 70, or 70 minus 40, because you can go in the other direction as well. It's just the stepping size. Again, we don't have to use a formula because they didn't give us any information about the population. They just said, you know what, we're going to do all that work for you. And they already gave us the distribution of all those means that were collected. Now they're asking, so part B is a little tricky. So they're asking if the sample size is 25, what's true about the shape of the population? Now the population does not correspond to this graph here. This graph is referring to the sample means, which was taken from the population.
Would it be what's called regular or evenly distributed because it's not 30?
So it's so this is where it gets a little tricky because it's not 30. Yes, so n is not 30, which is a good observation to make. But something to note is that the I thought it said something about the sampling distribution being normal. It's kind of assumed. So this is the reason why this is tricky is because this uses an idea from logic called it's a contrapositive. So you'll never have, unless you take a philosophy class or a logic-based class, it's basically using the definition above. And it's saying, if you're able to take such a small amount of samples and still have a normal distribution, then your original population was probably normal in the first place. Because you couldn't get normal from this with that view of trials, of samples. So that means, so it's, again, it's a little bit more logic-based, which is why I wanted to talk about it here. The population has to be normal. Because if the population was not normally distributed, then only doing the study 25 times would not be enough to make the resultant sampling distribution also normal. You would need more. So it has to be normally distributed. Now, if that N was 35, then you wouldn't be able to make that assumption. Because 35 is past the 30 sample threshold, which means the population could have been normal or not normal. It doesn't matter. Your sampling distribution will be normal no matter what. So again, that's kind of tricky. If you're interested in logic, there's something called a contrapositive, might be kind of interesting. So they go on to say, given N is 25, what is the standard deviation of the population? So they want us to find the standard deviation of the population. The standard deviation of the population is sigma, just by itself. Standard deviation of the sample mean is the sigma with the little X bar at the bottom right. But they're not asking for that. So they're switching it up on us. We already found that out. So we need to figure out sigma. So we need to find sigma. So how do we find sigma given everything we know? Well, what formula do we know? Well, we know that sigma of X bar is equal to sigma divided by the square root of N. We talked about that formula on the previous page. And we know all these values but sigma. The sigma of X bar, the standard error, we found to be 30. 30 is equal to sigma divided by the square root of N. What's N? Oh, they tell us right there, it's 25. Oh, so that's just a little bit of algebra. In fact, it works out even more nicely because the square root of 25 is just 5. So sigma is equal to 30 times the square root of 25 after you solve for sigma. So really that's just 30 times 5, which is 150. This calculator's been here for years. I think it finally just met its days. Oh well. Okay, so let me just make sure that. I think it's kind of early. 150, so that's it. That's the standard deviation of the population given the standard deviation of the sample mean. Does anyone have any questions about this problem before we proceed? Again, the computations are very simple. It's just very dense having to deal with two different means at the same time, two different standard deviations at the same time. But if you're ever looking for the mean or the sample, or let me start. If you're ever looking for the mean or the standard deviation of the sample means, they will give you a sample size. Because in this problem, they gave you the resultant graph, but you need the sample size in order to, well, use the formula. How can you use the formula if you don't have a lowercase n? So expect that information for this section. Let's move on to example 3 here. So since we know that if you take all those averages from each sample that you do, and you put them on a graph, provided you do enough samples, you will get that the sampling distribution is normal every single time, which is fantastic because we get a lot of assumptions from that, which basically means that we can treat the collection of sample means as a normal random variable, which means we're going to go right back to all the stuff we did in the last section. So this is where that natural cumulative aspect of math comes into play. But if you already printed out the notes, you might see that we're not going to really use that table anymore. Remember that table in the back of the book? We're gonna cut that out. We don't have to use the table anymore. And we'll talk about how to use the calculator instead. I know some of you have already figured out how to do it in the calculator, and if so, that's fine. We're going to talk about it here as well. So I'm going to talk about how we would do this if we had to use the table, and then compare this to how we're going to use the calculator. So example 1, we were talking about IQ scores. I'm going to go back to that example. Means 100 for the population. Standard deviation is 15. We're going to go right back to example 1. And so it starts off the same way it would for a standard problem in the previous chapter. What's the probability that a person has an IQ less than 95? So you would have to understand that this is x is less than 95. The probability of x is less than 95. You would have to find the z-score. So hopefully you all might remember from before spring break. You take the score itself, you subtract by the mean, which is 100, and you divide by the standard deviation. (95 minus 100) divided by 15. We would need, so this would not be the answer, but instead would be what goes here. About 2 decimal places, so we would be able to use the table. So for this problem, this is going to be the last time I use the table, the last time you all have to use the table. Since z is less than this number, we can use the table directly, and we have a z-score, so we just need to find the z-score and determine the corresponding area. Negative 0.33. We go down to the table. Negative 0.33. Here's the row. And then 0, 1, 2, 3. I believe this one would be it. And we get the area as 0.3707. 3707. And that would be the probability. So that's how we would have done this in the previous chapter. So, and the way we would interpret this, so you might remember this from the previous chapter as well. We figured out the probability, and they say, well, interpret this for 100 randomly chosen participants. So if there were 100 participants and we know that 0.3707 exhibit a certain characteristic, and we're just multiplying. 37.07. But we're talking about people, which is discrete, i.e. it's a positive whole number. So we're going to be talking about 37 people. Have an IQ less than, because it did say less than. Not exactly or greater than, they asked for less than. And so that's how we would have done that before. So far, hopefully that's all pretty familiar stuff. So again, it's going to be the last time we have to use the table. Now we're going to switch. So nothing we did has been, for this problem, has been specific to this section. So now notice how they give us a random sample of 20. So what they're doing is they're telling us that n is 20. And normally when they give us a sample size, we're finding sampling distribution measures. Now, they're first asking is, will the sampling distribution of the sample means, is that going to be normally distributed or not normally distributed? Now, the n being less than 30, that would be a problem, but IQ scores are inherently normal. So we get normality for free. It doesn't, when you know that the population is normal, then you know that the sampling distribution will be normal no matter what the sample size is. So this will be normal because the population is normal, not because of n is less than 30. So this is because population is normal. You just get it automatically. If the population is not normal, then you require that n has to be 30 or greater. That's pretty much the yin and yang of it. And then they want us to find what the sample mean is, or the mean of the sample means, and the standard deviation of the sample means. Well, we know that the mean of the sample means is simply whatever the mean of the population is, which they gave us. It's just 100. They told us at the very beginning, it's just 100. There's no computation for this part. It's just derived from the population, for the parameter of the study. So that's 100. Now, what about the standard deviation of the sample means? You need the standard deviation of the population, and then you divide that by the square root of the number of, well, your sample size. Well, they told us the standard deviation was 15 at the very beginning. And then they said that the random sample here is 20. They said that suppose a random sample of 20. They immediately told us that n is 20. So we can figure this out pretty quickly. $15 divided by square root of 20. I believe it's best to put this, or they might ask for this in 4 decimal places. Let me check. I know I wrote it down here. Yes, they want 4 decimal places. So we have the mean and the standard deviation. And we can go ahead and fill in the blank for the second one here. 3, 5, 4. Oh yeah, and it says 4 decimal places right there. Okay. Now we have the mean and the standard deviation for the sample means. And from here, notice now in part D and E, they're asking the same questions from before. At the most, 104, which would mean, of course, X is at the most 104. So you would normally have to go about finding the z-score, doing this, find the z-score, make sure the inequality is facing the right way. We don't have to do that anymore. You still set it up as P is X is less than or equal to 104. But now we're going to use one command in the calculator called normal CDF. And normal CDF, we go ahead and scroll down right fast to the calculator tutorial here. So, well, depending on which calculator you have, you might have to do something slightly different, but the process is going to be almost identical. If you have the newer calculator, it might be even easier for you. If you have the old one, that's what I'm going to be working off of here. So if you press second and vars, vars is right under, well, right next to clear, right under the bottom cursor on your calculator. So vars is right here. And if you click on it, you will see, well, it says at the top DISTR, distribution, and you want to move your cursor to the second one. We are not going to use normal PDF. We're using CDF. So far you should be here. Now, depending on which calculator you have, if you have the more primitive one, like I have here, you're going to see simply this. If you have the newer calculator, you're going to see, it's going to say lower, upper, well, mu, which is population mean, and sigma. No matter which calculator you have to figure out those four values. And there's three different situations. There's three different situations you have to worry about. The first one is if your inequality is a less than or equal to sign, you do the same exact thing. The second situation is if you have a greater than or equal to sign. The third one is probably the easiest one, if you have a compound inequality. I have all the situations listed here. Our example is the first one, because remember, scroll back up right fast, x is less than or equal to 104. Okay, so x is less than or equal to 104. So I'll put that here, x is less than or equal to 104, which does fit this right here. Now, if you do it this way, the lower is always going to be negative 10,000 in this situation. Because if you have x is less than a number, well, what's the smallest number in that inequality? There's not really one. So we need to kind of trick the calculator. And I just say, I saw this online, I thought this was a good idea. Just put negative 10,000. It might say negative 1E99. Just get rid of that. It doesn't scale very well. Just put negative 10,000. So if yours says negative 1E99, that would work as well, but don't just put negative 10,000. That should be perfectly fine here. Now, if you have the primitive calculator, this will be the first number you type in, negative 10,000. The lower is always what you put in first, and you have to put a comma if you have the primitive calculator. And if you have the newer one, you just put negative 10,000 next to lower and press enter, and it'll bring you to upper. Now, upper is the value in your inequality, which was 104. Because x goes all the way up to 104. That's the upper bound. So for primitive calculator people, you type in 104 and a comma. For newer calculator people, you type in 104 for upper, and you press enter. Then it'll ask, the next thing you have to find is the mean, which we actually found in part C. We're using the mean of the sample means and the standard deviation of the sample means. Those are the next two numbers. No matter what inequality you have, those are always the last two numbers that you put in here. So this part's not going to change. The mean was 100, comma, or on your calculator, you just put 100 next to mean, and then 3.3541, and close your parentheses. And if you missed any of that, the example is based off of the previous example, so you can follow along if you missed a step there. In any case, old calculator, new calculator, you should get 0.883, blah, blah, blah. So again, I'll write that here, negative 10,000, 104, because 104 comes from the inequality itself. The mean we found above is 100, and the standard deviation of these samples was 3.3541. That was 0.8835. They normally want 4 decimal places. And right above this, oops, I'll put what all of these mean. This one was lower, upper, and then mu, well, technically mu of x, and sigma of x. That's what it's going to want in a situation where we have a less than or equal to sign. If we have a greater than or equal to sign, you're going to switch the first two values and do something slightly different, as we'll see here momentarily. So far, does anyone have any questions before we look at part E? If not, let's go ahead and look at part E. Because part E says greater than 98. X is greater than 98. P is greater than 98. So the inequality sign flipped. Now, you do not have to go in and flip it back, because normally if we were using the table, you would have to find the z-score and flip the inequality, which means you would have to subtract from 1, subtract the probability from 1. You don't have to do that with this calculator anymore, but you have to know how to rewrite it accordingly. Now, we're still going to use normal CDF. The only difference is lower and upper are going to change. The last two do not change. Now, lower, in our inequality, x is greater than 98, and that, if you think about that on a number line, what's the smallest value that x can be? 98. So it does say down here, so this is example, this is the second situation. This is P where x is, what was it, 98, greater than 98. So really that's this example right here. Notice the lower is whatever the value in the inequality is. So that would be 98. The upper is default at 10,000, positive 10,000. We need a positive number here because we're going greater than. I believe if you put in a negative number, it might throw an error at you. And then the mean is the mean, the standard deviation stays the same as well. So that's the only thing you have to switch. If the inequality switches in that way, you have to switch lower and upper. So 98 for the lower, 10,000 for the upper. The mean and the standard deviation stay the same. And notice there's no subtraction from 1, nothing like that. If you put it in the calculator the right way, in fact, if you press second and enter, you can just bring up what you had before and fool around with that. 98, comma. Type in everything correctly. You get about 0.7245. So that's what happens when you have a greater than sign. The lower value is already in the inequality, and the upper value, since x is greater than 98, technically it increases forever, but we need to trick the calculator. And the best way to trick it is just to feed it 10,000. We won't be dealing with numbers that come anywhere close to that. Any questions up to here? Again, notice no table. In your homework, you will have to use the table for maybe when they introduce this stuff, like I did in part A and B, well, mainly part A. But after that, you don't have to use it anymore. Okay. And then there's the last situation. What about if you have a compound inequality? between 96 and 108. So 96 is the smaller one, 108 is the larger one. And this one's honestly, in my opinion, the easiest one, because we don't have to trick the calculator here. We know what the bounds are. We know what the lower bound is. We know what the upper bound is. The lower bound is 96. It's the smaller number, and the upper bound is 108. So there's no need to use any extreme values. So then the mean and the standard deviation of the sample mean stays the same. So we have lower and upper, and U of X bar and sigma of X bar. And from this, let's go back to 96, 108, delete. Make sure these numbers come out right. 8749. So in case you forget, the following calculator tutorial, again, is completely predicated off of the previous example. So if you're confused about where these numbers are coming from, please go back, reference the notes, and try to follow along with that to make sure you get the same numbers. And my decimals line up perfectly with the example I provided here. Does anyone have any questions before we move on? If not, let's go ahead and do exactly that. Okay, move on to example 4. So we're basically going to do all this again, just for practice, and add something a little bit different as well. The shape of the distribution of the time required to deliver a pizza in Hammond is, let's just say we don't know. We have no idea. But company records show that the mean time, just in general, is 31.3 minutes with a standard deviation of 4.5 minutes. What is the mean and standard deviation of the sampling distribution of X bar? Now, if you printed out the notes, please put that n is equal to 45. I did not put that. So please go ahead and add that to your notes as well. So no, because you can't figure out the mean and the standard deviation of the sampling distribution if you don't know the sample size, because you won't be able to figure out the standard deviation. You won't have the n. So to figure out the mean, well, the mean of this is simply just the mean of the population. Mean time is 31.3. Oh, that was easy. 31.3. Okay, that's already one right there. What about the standard deviation? Well, that is the standard deviation of the population divided by the square root of n. Again, this is why you need to have that assumption for the sample size, or else you can't use this formula. So they said the standard deviation is 4.5. The square root of, well, 45. And here, I believe they want us to round to 4 decimal places. So we can do that right fast. 4.5 divided by the square root of 45. .6708. Now with these problems, it is expected. I think there's one homework problem where they don't have you do this first, and then they just start immediately asking you questions. You definitely want to figure out the mean and the standard deviation of the sampling distribution quickly, no matter what. Provided, as soon as they give you the sample size, you need to go ahead and compute those values, or else you're going to be getting wrong values if you try to use the population values. Mainly the standard deviation is going to be different. So notice again, they have the same premise as before, at least 32.7. This is the probability when X is at the least 32.7. So notice I'm taking the wording, I'm converting it to an inequality, and from there I can feed it straight to the calculator. This is normal CDF. We need a lower, an upper, the mean, and the standard deviation. So what's the lower in this example?
32.7.
Yeah, it's 32.7. That's because if you think about this inequality on a number line, 32.7, if X is greater than or equal to that, it goes this way. What's the lowest part of that shaded region? It's the 32.7. What's the highest part of this? Well, there's not really one, so we just kind of put 10,000. Just something really large and positive. And technically, that 10,000, you could put 100,000, you could put 1,000,000. 10,000 is chosen somewhat arbitrarily. So we put 10,000 just to give it a very large upper bound that will not cut off things too quickly. When they have that -1e to the 99, that's a very, very, very small number, as you would imagine. But we don't need it that small. All right, so there's the upper. And the mean and standard deviation follows straight from what we found in part A. So we just simply feed it to the calculator. So I imagine you all wish you had this versatility to use for the last exam. Now you get to use it here. 32.7, 10,000. 31.3, 0.6708. 0.0184. Just simple, as simple as that. Okay, so that's that one. Let's keep going. And basically, when it keeps saying n is equal to 45, that means we keep using the sample, or the mean of the sample mean and the standard deviation of the sample mean that we found earlier, because those values are based off of the sample size. If they changed n equals 45 to n is equal to 55, we'd have to find a new standard deviation, because that standard deviation is based off of the sample size. Basically, the repetition of 45 means we can keep using that standard deviation we found. So less than 30 minutes, probability of X is less than 30 minutes. Again, we feed this straight to the calculator. The lower, well, X is less than 30. It'd go less than forever. So we'll put a lower bound of -10,000. The negative to make it very, very low. The upper is 30, which is in the inequality. The mean and standard deviation carry over. I'll just go ahead and grab the result from before. -10,000, 30, 31.3, and 6708. And we get 0.0263. So is this coming together pretty nicely? Is this calculator thing very helpful? Part D, they do ask, is the result in part C unusual? Unusual means is the probability less than 0.05? So I know I asked this as a test question. That's what it means. It's when the probability is less than 0.05. Well, yes. Because 0.0263 is less than 0.05. What do you conclude from this? I'm trying to remember. It's something about the population mean. I kind of manipulated this problem from another one. It said something about whenever this happens, the predicted mean is higher than the population mean. I think that's what it said. And the predicted mean is the mean that's based off of that database mean that they provided. Now, part E, they don't really say anything about minutes, but instead, they'll give a bonus for each pizza delivered under a certain time frame. Let's say that this is going to happen 15% of the time. We don't know the time frame. They're not telling us the time frame. But the boss wants it to be a little bit more difficult to get a pizza delivered in that time. So he's going to look at the previous data and give this bonus whenever this happens, which is a 15% chance of happening. We need to find the time frame that corresponds to the probability of 15%. How do we do that? They're not giving us the time frame, so there's no inequality here. So what they're doing is they're telling us that the probability is 0.15. This is what's given. So now the question is, well, how do we do that in the calculator? Well, you have the notes printed out. You might have seen already. There's another calculator command. This one's only 2 steps, though. When you're given the opposite information, and you've seen problems like this in the previous chapter, and this would have been very helpful for you, you use something called the, oh, I didn't change that in the notes, not normal CDF, inverse norm. That's what you want to put it on, inverse norm, which the picture's right, the statement's wrong. Everything else looks right, though. So you're going to use the inverse norm, and you need 3 values, regardless of which calculator you have. So inverse norm is right next to, normal CDF. It's 1 below. And again, if your calculator's fancier, yours is going to say, give us 3 values. You need the area to the left, the mean, and the standard deviation. Well, guess what we have? We have the area to the left, 0.15. You need the mean, which was given in, well, part A, and we've used it in parts B and C, 31.3, and then the standard deviation. So you only need 3 values this time. There's no lower or upper.
Mine is asking left, center, or right.
Do left. Keep it on left. Yeah, so if your calculator is fancier and it asks for left, center, or right, keep it on left. And so this would correspond to the number of minutes. 6, let's just say 6. Wait, why do I round? 60. Just keep it at 2 decimal places. So this is going the opposite direction. We're given the probability and have to find the time in minutes. Does anyone have any questions about this? Not. Stu, we just did all this, so let's look at one more problem. You might recognize this problem. Pretty similar to the game where you spin the wheel and you drop the ball in, and it has a probability of landing on something. It's very similar to that. First thing they want us to do for this is construct a probability distribution function. Now, you win $60 if you pull one correct card from a deck of 52. Well, there's a 1 out of 52 chance of that happening. So if you do that, you win $60. What is that value? It's not a very likely probability. And so what's the chances of this not happening? Well, there's 51 cards working against you. 0.9808. That's the probability distribution. Just very simple computations. Now they want us to determine the mean and the standard deviation of this data set. Now, this isn't asking about the, this isn't giving us a sample size. This is just asking for us to determine the mean and the standard deviation. Oops. So this is where one thing we could do, put this in the calculator right fast. 0192.9808. And do the one variable statistics. On L1 and L2. So we did this before. We did this in the previous, this is the one variable statistics, L1 and L2. The mean is 0.1712, standard deviation. .3709. So these are more population values. So I'm going to put population symbolism, because from here, we need to figure out the mean and standard deviation of these sample means after you play the game 100 times. Now the mean carries over, the standard deviation almost does. But we have to divide by the square root of 100. Which is going to be 0.83709. The square root of 100 is 10. Any number divided by 10, you move the decimal place over one time. And then they ask for when the sample mean is greater than 0, or n is equal to 100. Which means you plug this straight into the calculator for the normal CDF. This would be 100. We'd use 10,000 as an upper bound. The mean is 0.1712. The standard deviation is 0.83709. so close to finishing. I am out of time. So I'm going to push this homework back to Thursday, but I am very close to being done with it. So I'll wrap it up there. If you are curious though, for part E, you would have to find a new standard deviation because they changed the n value on it. Other than that, sign the roll sheet if you didn't sign it already. That's all I got for today. Have a good day.